6.3 Orthogonal Projection. Recall the following result. Suppose we have two vectors u and v in Rn, and the line L is formed by the vector u. Then the vector on L that is closest to v is the orthogonal projection of v on L. This is L and this is v. The vector that is closest to v on the line L is the orthogonal projection of v on L. So this w vector is the vector that is closest to v among all vectors on L. The problem that we are going to discuss here is as follows. Suppose v is a vector in Rn and w is a subspace of Rn. And we would like to know what is the vector in w that is closest to v. Suppose this is w and this is the vector v. And what is the vector on w that is closest to v? And later we will define something called orthogonal projection of a vector on a subspace. Orthogonal projection on a subspace, and this vector is the vector that is closest to v. So this orthogonal projection of a vector on a subspace is something that we are going to define later, and we will show that that's the vector that is closest to v. This result can be very useful when we talked about more general sets in chapter 7. In chapter 1 to 6, what we are talking about is Rn. The sets that we are concerned with is Rn. And in each Rn, these are vector. These are n-tuple vector. But in chapter 7, we will be talking about more general sets. So this, for example, could be sets of function. This is a function. And w could be a set of polynomial. And the vector that is closest to a function ft would thus have the interpretation of the best approximation, the best polynomial approximation of f of t. This is something that we were talked about in chapter 7. Although orthogonal projection is the main topic here in 6.5, it does not enter the discussion until later. We will take a sort of roundabout way to the introduction of orthogonal projection on a subspace. We will first define something called orthogonal complement, and we will discuss property of orthogonal complement, and then we will make a connection with orthogonal projection later. The orthogonal complement of a non-empty set S of Rn. S is a subset of Rn, and the orthogonal complement of S denoted by S perp. This notation reads perp. It is the set of all vectors in Rn that are orthogonal to every vector in S. We can describe S perp like this. It's the collection of all vectors in Rn such that it satisfies the property that it's orthogonal to every u in S. For example, S is the set of all CV and R2 for all C in R, and V is a non-zero vector in R2. For example, S is the line formed by a V vector in R2, a non-zero vector. So this is a S. What would be S perp? Pause and think about this. What is S perp? S perp will be the line that is perpendicular to S. How about the case that S is Rn? What would be S perp? The set S perp is the collection of vectors that is orthogonal to every vectors in Rn. And S is Rn, so there's only one possibility for S perp. The zero vector is orthogonal to every vector in Rn, and that's S perp. How about the case that S is this set? There's only one vector, and that's the zero vector. What would be S perp? Well, in this case, any vector in Rn is orthogonal to the vector in S. So S is Rn. Another example, S is the xy plane of R3. So this is S. It's the xy plane. So we can write S as the collection of all vectors in R3 that is of the form A, B, and then 0. What would be S perp in this case? X perp would be the z-axis. It's of the form 0, 0, C for all C in R. Let's show this. If we have a vector in S perp, this V vector is in S perp, if and only if V is orthogonal to every vector in S perp, so it's orthogonal to all vector of the form AV0. And this means in particular that AV1 plus BV2 is equal to 0 for all AB in R. This is true for any scalar A and B. So, in particular, it will be true when A is 1 and B is 0, then we get V1 equal to 0. And if A is 0, so this will go away, B is 1, we get V2 equal to 0. So, V is of the form that the top two entries are equal to 0. So, S perp is of this form. It's simply the z-axis. Now let's talk about some property of S perp. Suppose S is a non-empty set of Rn. Is S perp a subspace? For this we need to verify if 0 is in S perp, and if we have two vectors in S perp, is there a linear combination also in S perp? Well, the first one is no problem. 0 vector is in S perp because it's orthogonal to every vector in S. For the second one, if we have UV in S perp, that means in particular that U transpose is orthogonal to every Z vector in S, and V transpose is orthogonal to every Z in S. Does this imply the linear combination is also orthogonal to every Z in S? And that's indeed the case, right? So this is yes, and yes, and yes. Now suppose S is a non-empty subset of Rn. It has V1 to Vk, k vectors. And we know if U is a vector in S perp, then U is orthogonal to every vector in S. U and V dot product is equal to 0, and this is true for all V in S. Now the question we have here is this one. Is it also true when U is a vector in S perp, then U dot product V is equal to 0 for all vector in span S? So here we have Rn, and we have S, which is a small set, and we have S perp. This is S perp. S perp is orthogonal to every vector in S, and we also have span S. This is a span S. The question now is, we have U in here. U is orthogonal to every vector in S. Would it also be orthogonal to every vector in span S? That's the question. We know for every vector in span S, it can be written as a linear combination of the vectors in S, V1 to Vk. Now let's consider the dot product of U and V. If we perform that product, we get U transpose V1 and U transpose V2 and so on and so forth. But what is U transpose V1? V1 is a vector in S, and U is a vector in S perp. So if we have the dot product of U and V1, we get 0. And similarly, for all the other terms, we get 0. So this is a 0. So indeed, if U is an S perp, U is orthogonal to every vector in S, then U is orthogonal to every vector in span S. Because U is orthogonal to every vector in span S, that means that U is in fact a vector in the orthogonal complement of span S. Well, if the fact that S is in S perp imply U is in span S perp, then which one is a larger set? Which one contains which one? Span S perp contains S perp, or S perp contains span S perp? It is this way, right? We would like to ask if the other way around is also true. So this is Rn, this is S, this is span S, and span S perp is a set that is orthogonal to every vector in span S. Every vector here, every vector in the blue set is orthogonal to every vector in the black set. So in particular, it will be orthogonal to the vectors in S. So if U is a vector in span S perp, U is also orthogonal to every vector in S perp, every vector in S, so U is also in S perp, and that will make this true. So yes, indeed. So if we combine these two facts together, then we get the result that S perp is the same as span S perp. And this is true whenever S is a non-empty finite subset of Rn. here we have Rn, and this is S, this is span S, this is S perp, and this is Z is in fact the same as span S orthogonal complement. There's an interesting property about the intersection of span of S and S perp. So it's the blue and black sets intersection. What would be the intersection? Well, if we consider vector in the intersection, then this U vector, suppose we have a U vector in span S, and U is also in S perp. Let's see what kind of property U has to satisfy. Let's try to compute the norm square U transpose U. We know U transpose U is in S perp. U is in S perp. And we also know U is in span S. In span S. Just now we saw that S perp is the same as a span S perp. So now we have the dot product of a vector in span S and a vector in span S perp. So what would be this dot product? It would be 0. What does this mean about U? U transpose U is equal to 0. That means U is the 0 vector. So the intersection of span S and S perp has only one vector, because whenever a vector is in span S and it's also in S perp, it's always the 0 vector. So the intersection is the 0 vector. A question? Suppose S is a basis for a subspace V of Rn. How would S perp and V perp related? A result that we just saw can help us on this, right? Which result is it? Because we know S perp is in fact the same as span S orthogonal complement. And span S in this case is V. So this is actually the same thing. So one direct effect of this is that if we want to find V perp, the orthogonal complement of a subspace, we can instead find S perp. And finding S perp is usually easier. Why? Because S is a basis, there are only so many vectors, a finite number of vectors in S. So if we want to find S perp, we only need to find vectors that are orthogonal to the finite number of vectors in S, which is usually an easier job to do. Let's look at an example. Suppose W is a span S, and S is this set, U1 and U2 vector, where U1 is this one and U2 is this one. And we would like to find the basis for W perp. And using the results that we just had, we know a vector is in W perp if and only if it's in S perp. S has only 2 vectors, so V is in S perp if and only if V is orthogonal to U1 and V is orthogonal to U2. Combining these two equations together, we get U1 transpose U2 transpose V equal to 0. Let's call this matrix A. And what does this mean? This means AV is equal to 0, a homogeneous equation, something that we are already very familiar with. And this S vector is in S perp if and only if it's in the null space of A. V is a vector in S perp if and only if V is a vector in the null space of A. So now we know how to find null space, right? S perp is equal to W perp equal to null space of A, and we know how to find the basis for a null space. On the other hand, we can take another look at this construction. We see that the column vectors are the row vectors of A are U1 transpose and U2 transpose. So how would W, which is the span of U1 and U2, related to A? Related to some subspace of A? Column space, row space? It's the row space, isn't it? W is the span of U1 and U2, so W is actually the row space of A. W is the row space of A, and W perp is the null space of A, so the orthogonal complement of row space of A is the null space of A. In this example, row space of A and column space of A are orthogonal complements of each other. If this is true in general, the row space of A and the null space of A are orthogonal complements of each other for a general n by n matrix, for any n by n matrix. We will leave this as an exercise.